The next speaker is Katie Vandorou from the University of Tasmania. They will be speaking on the combined power of microlensing and Keck adaptive optics for exoplanet mass measurements.
So hello everyone, my name is Katie. I'm a PhD student at the University of Tasmania in Australia. This is my first conference talk actually, so thank you very much for having me. So gravitational microlensing is one way that we can detect exoplanets. And a very simple description of what the method is that as light from a background source passes through the gravitational field of a star or lens, as we call it, it will be amplified. If the lens also has a planet in the right place at the right time, it will create an anomaly on the light curve. So gravitational microlensing relies on a chance alignment between a background source, a star with its planet, and us, the observers. So it can be quite difficult to find a planet in this way. But the reason why a community of about 100 astronomers or so continue using this method is that it greatly complements other detection techniques like radial velocity and transits, because it has the ability to detect planets over a large range of masses and orbits, bound or unbound to their host. And it is even sensitive to planets orbiting stellar remnants. And the main reason for this is because in microlensing, we get most of our information from the amplified light of the background source. But because we're not actually detecting the light of the lens, so the host star directly, it's difficult to accurately determine the mass and distance of the system. And this is where Keck adaptive optics comes in. So if we wait several years after the initial detection has taken place, the relative proper motion between the source and the lens may be large enough that they can be resolved. So using telescopes like Keck, we can see the separation. So this image here is a good example of what a resolved source and lens look like. So this is an event that we've been working on. It's just recently been published, MOA 2013 BLG 220. Where we took Keck observations 6 years after it was observed in microlensing surveys. And in the detection paper, they predicted a separation in 2019 of about 72 milliarc seconds, and we observed, in our Keck images, we observed a separation of 77 milliarc seconds in 2019, which was great. So we measured the flux of the lens directly, as well as the amplitude and direction of proper motion, which provides additional constraints for mass measurement. And then using mass distance relations, we could figure out the mass and distance of the lens star, which we can then use to find the mass of its planet. Of course, not all events that we observe have a lens and source so resolved. Sometimes we need to use Deophot or other PSF fitting tools to figure out what's going on. But in practice, with a full width half maximum of about 50 milliarc seconds, and with a lens and source of comparable brightness, we have been able to constrain their relative fluxes and relative proper motions, even if they're separated by only 20 milliarc seconds. So using a combination of these instruments and filters starting in about 2012, which was long before my scientific career began, the team has observed about 80 different events with Keck. And for some events, we've even gotten simultaneous Hubble Space Telescope data, which was really cool. So here are a couple of our most recent examples. Of course, MOA 2013 BLG 220, which I mentioned. We resolved the source and the lens with Keck's NUC2 adaptive optics system and managed to get a magnitude for the lens star. So these histograms here are distributions for the Bayesian posterior probability of the lens star and planet's mass, distance and separation using properties from both the original light curve model without Keck constraints in blue and with Keck constraints in red, so you can really see the difference. And we found that the system is made up of a super Jupiter in a wide orbit of about 3 AU around a solar type star, 7 kiloparsecs away from us. So the discoveries of microlensing events can make estimates for the lens mass and distance, but they just lack the additional constraints of having a directly measured lens flux. So this is MOA 2007 BLG 400, which was led by Aparna. For this event, again, we managed to observe the lens, which is about 2.5 magnitudes fainter than the source, so it's a little trickier to see. But we managed to get a magnitude and constrain the physical properties of the system, and we found that this is another super Jupiter orbiting a K-type star. So what's interesting about 220 and 400, these two events, is that they have similar mass ratios, and the Keck observations have shown lens masses that are higher than the predicted distribution. And this predicted distribution is based on an assumption, which is that all stars of all masses are equally likely to host planets of a given mass ratio. So these results for 220 and 400 suggest that this assumption is wrong. So a major part of these observations with Keck is to also try and test any assumptions that are made in models. And of course, the more events we observe, the more data we get, the better. Another big reason as to why we are conducting high resolution follow-up observations with Keck is to refine the mass measurement method, which will be routinely used for a larger sample of exoplanet lensing events with the Nancy Grace Roman Space Telescope, which is currently under development. The Roman Space Telescope will have the capability to observe free-floating planets as well as detect planets that have Earth or Mars-like masses and wide orbits, which we don't have a lot of information on. It will also have a very stable PSF, and it will be able to measure the separation of source and lens very accurately. And it will be able to do this for all stars, even the really, really faint ones with magnitudes above 21 or 22. So using Keck, we're figuring out the best way to reduce the images, measure photometry, which models and error estimate methods work best, and we hope to fine-tune this method and then use it on a larger sample. But to test what WFIRST will do tomorrow, we have to first do it today with Keck. So thank you very much for listening, and I guess I'll take questions now.
Katie. Yeah, so while we wait for questions, and again, you can ask either through Slack or through the Zoom on the chat or the Q&A. I wanted to ask, what is the limit for the planets that you can detect with Keck?
With Keck, we have, well, I guess it depends on the lens, on the magnitudes of the lens. But yeah, with Keck, we can't typically detect a lens that is above like an H magnitude of about 21, because it's just too faint. But ground-based microlensing surveys, they reach their limit at about Earth, like super Earth masses, or sub-Saturn, sub-Neptune masses. So yeah.
Great, thanks. So there is a question here, a quick Q&A from Jason. How do you tell which star is the lens and which is the source when you resolve them?
So because we already have the observations taken from the microlensing surveys previously, usually we have precise measurements of where the source is. Sometimes with Keck, we've done several years of observations, and we know how bright the source is. So it's kind of like looking at the stars, and we say, well, we've measured this brightness for this star, and that matches what we know the source star to be.
Okay, thanks. I don't see any other. Oh, wait, there is another question here. Click in the Slack. Could you use multi-band photometry or spectroscopy during lensing and then shortly after lensing to decompose the lens or source spectral types?
You could. We haven't done that already, but looking into the spectra of the lens star is of great interest to us, and we're planning on writing several proposals in the future for different instruments. Because yeah, that would be really, really cool to get data on that.
Okay, great. Thank you. If there's any other questions, please ask in the Slack.